So here is some set of pictures which we will make use of, but let us for a second try to understand what is shown here. Again, here are two complex planes of T. This is a complex plane of T, and this is a complex plane of T. So first of all, two pictures correspond to two slightly different values of independent variable z. And recall that on the previous slide we realized that on the complex plane of z now, if z is real and positive, only one saddle point contributes to the integration path, and when z is real and negative, two saddle points contribute to the asymptotics. And of course, we understand that if we try to change argument of z continuously, at some point one should change to 2 as a discrete process. So it happens, of course, at some very precisely defined line. And our goal now is to search for this line and to understand exactly what happens when we cross it. So, and the answer is the following, that this change from 1 to 2 happens on the so-called Stokes line. Here it is. And in fact, there are 3 Stokes lines for the area function, 1, 2, and 3. And each of this line, potentially, the number of contributing saddle points can change. Let us think how it looks like in practice. So to be more specific, this picture corresponds to z slightly before the Stokes line is reached, and this curve corresponds to z slightly after the Stokes line is reached. So here the argument is slightly less than 2 pi over 3, and here the argument of z is slightly larger than 2 pi over 3. So let us now again recall what is shown here. So on this complex plane of T, the regions where the integral is convergent are dashed, and they are of course identical at both of these pictures, as the contour itself does not depend on z. But now this set of green lines and green dots correspond to stationary points and constant phase trajectories. So first of all, for stationary points, these are these fat green dots. And you see that if you compare these two pictures, the position of these dots itself almost doesn't change. And this is natural, as these points, t equals plus or minus square root of z, changes smoothly as you vary z. And when you go from this point to this, the location of these stationary points themselves changes only slightly. So, but if you inspect these figures more closely, you see that the configuration of these green lines changed a lot. And in particular, let's try to understand how we are going to deform our original integration contour, which goes like that, remember, both here and here. How do we decompose it into a set of stationary paths? And let us start from this situation. Remember that this situation corresponds to argument which is slightly less than 2 pi over 3. Then let us consider what are our options. So the most naive option is to do something like this, to start from this green line somewhere here, go across this green line smoothly, like this, and then go to infinity. And of course, this trajectory is very reasonable. Why? Because it starts and ends at the regions where the integral converges, and it passes exactly through the stationary point. So far so good. It seems that this is consistent with our understanding. Indeed, in this region, only one saddle point contributes, but let us try to understand the reason. So in particular, let us try to see what happens if we try to catch both of the saddle points on a single stationary phase curve. So what happens is, suppose we try to start from this stationary phase line, go like this. So it means that start from this point and go to infinity in this direction. And from the first side, everything is okay. We started and ended in allowed regions and passed through the saddle point. But now we need to continue our integration path, and our area function is defined up to a contour which starts and ends in these regions. So suppose we reached here and we start to move from this region in order to achieve our final destination. So far our path is like that. But if we try to leave this allowed region by a stationary phase line, we see that this is possible only if we leave the allowed region and as such end up our integration in the region which is forbidden. And of course, this is not something which we can afford. It means that the only contour which is allowed for this situation is like this. Okay. With this logic, we understand that with this configuration of the stationary path, the only option is to catch one saddle point, and in particular this one. So let us now turn to the second picture, which corresponds to argument which is slightly larger than 2 pi over 3. And again, we need to start from this region. And let us see what are our options. So suppose we started like that. Then we can be smooth and reach, moving across the stationary phase line, reach another infinity. And the most important difference compared with this case is that now we can, starting from this region, go across the stationary phase line and reach to our final destination. And this path, it satisfies all what we want. In fact, first of all, it starts and ends in the proper regions, and it goes always along the constant phase lines, and it catches both of the saddle points. So you see the drastic change. Only after a slight change of the argument of z, we have switched our integration path from this one to this one. And the most important difference is that for smaller arguments, it catches only one of the saddle points. Here, it's already smoothly goes for both of them. And as a result, here, 2 saddle points contribute. And of course, this remains true for some range of the arguments. And it happens that you can perform the very similar analysis for, say, for these 2 points, and find for yourself that indeed what happens in this line is very similar. And finally, the last line is this one. And you may find that the topology of this path potentially changes at each of this line by the very same mechanism. What you need to take from this is that in usual life, when you calculate the asymptotic by saddle point technique, you are interested only in the immediate vicinity of the saddle points. But you have always deal with the question, which of the saddle points do contribute and which do not. The answer to this question is determined by the full picture in its full glory. And you see that the answer can be sometimes non-trivial, because, say, you see here that a very tiny change of z leads to drastic changes. But afterwards, after you understood which of the saddle points do contribute and do not, you may restrict yourself, like say here, only by immediate vicinity of the contributing saddle point, which is only 1. And here you need to restrict yourself only to contribution of the immediate vicinity of the saddle point, which is just come in pair here. But from this so to say, topological analysis, you can always safely and firmly conclude which of the saddle points do contribute and which do not.